We've got a few more topics left to talk about in Chapter 1, and we'll take a look at those together. These will be ones that we'll also cover in the first few weeks of lab. Talk about scientific notation. We can have numbers like this one in chemistry. Let's say we have something that has a very, very small mass or volume, and in order to write that number correctly in standard notation, it can get fairly long, and we can have numbers that would actually start with 20-some zeros after the first decimal place and make a very, very long number. And so to make those easier to write, what we'll do quite often is move the decimal place to a place that's more convenient, to a spot right behind the first non-zero number, so that the number we're writing is a number between 1 and 10. Now that obviously makes, in this case, the number much larger, or for a large number like 1,000,000 or 50,000, it would make the number much smaller. And so to compensate for that, we'll say that this 0.000000, I might have said too many zeros, 0.000000723 is equal to 7.23 times 10 to the minus 6, because we made this number 6 decimal places larger by moving the decimal. And the same thing is true for large numbers. Let's take this number, 458 million. We can rewrite that as 4.58, but to do that, we've made the number smaller by 8 decimal places. So 458 million is equal to 4.58 times 10 to the 8th. And so quite often in chemistry we'll write numbers in scientific notation, or some books will call it exponential notation, and it'll be a convenient way of representing very large or very small numbers. Now temperature, most of you, from thinking about weather and your body temperature when you might have been sick when you were younger, think about temperature as being measured in Fahrenheit degrees. And that's a convenient way for Americans to think, because that's the way that most of us have been taught. Your body temperature, if you're healthy and normal, is 98.6 degrees Fahrenheit. The freezing point of water is around 32 degrees, and the boiling point of water is 212 degrees if it's pure water. If we change to a more scientifically convenient scale, the Celsius scale has been devised so that 0 will be the freezing point for pure water, 100 will be the freezing point for, the boiling point for pure water. And as it turns out, that makes the body temperature, 98.6 degrees, exactly 37 degrees. Now what I'll want to do in class, the next time that we meet, is work out an equation based on this information, and where we can convert any Fahrenheit temperature to Celsius, or any Celsius temperature to Fahrenheit. More often than not, in a chemistry class, when you're reporting or recording temperature, you will do it in Celsius degrees. Now that's not always the most convenient temperature scale. What makes it inconvenient is that there are negative temperatures both in Fahrenheit and in Celsius. The temperature can go below 0. So if we're in a point where we want to be able to multiply by temperature as part of a problem that we're solving mathematically, we need to use a temperature scale whose 0 is the coldest possible temperature. And as it turns out, the coldest possible temperature, the absence of all molecular movement, is 273 degrees below 0 Celsius. So if we add 273, actually 273.15, to any Celsius temperature, we'll be on a scale where the widths of the degrees on the thermometer are the same as Celsius, but the coldest possible temperature is 0 on that scale. And it's named after a scientist, English scientist named Lord Kelvin. That's the Kelvin temperature scale. Just from a semantics or nomenclature standpoint, we say that a temperature is so many degrees Fahrenheit or degrees Celsius. We don't use the word degrees when we talk about Kelvin. Your body temperature is 310.15 Kelvin. People sometimes will say degrees, but that's considered incorrect. I want to talk, and we'll try to show some examples of this in the lab about two different words that some people use to mean the same thing: accuracy and precision. Let's say I weigh 190 pounds, and I weigh myself on the scale at home and it says 196. That's not a very accurate scale. But if I weigh myself 10 times and it says 196.0 every time, then that means that there's no variation in the measurement that's caused by the scale itself or by the way I'm using it. And that means that my measuring method is very precise, even though it's not very accurate. So it's possible to be accurate and not precise, and it's possible to be precise and not accurate. And so when we report numbers, we want to report them to the best accuracy and precision possible, and we'll develop methods in the lab for doing this. What we'll do is, from a reporting method, especially to signify the precision, how sure we are of how many decimal places we have, is we'll write down significant figures. If I were to tell you that my weight is 190 pounds, you would assume I weigh somewhere in the neighborhood of 190. But if I say my weight is 190.5, then you'll assume that I weighed myself that day and that I used a scale that was precise down to at least a half a pound. And so we have this reporting method that gives not only the value of our measurement or our reported number, but the precision. And so what we'll do is we'll write down our numbers to a certain number of digits, and if there are zeros at the end of the number, they'll be counted as significant digits, as digits that we're sure of. If, notice I spelled if with two F's here, that means if and only if there's a decimal point somewhere in the number. So you say, how many people were at the concert? I say 50,000. I write it down with no decimal places. Only one significant figure. That means that 50,000 plus or minus 5,000 were there, plus or minus 10%. But if I write down 50,000 and I put a decimal point at the end, that means I'm sure of all five of those digits, that there was an exactly 50,000 person attended concert. So decimal points will determine whether zeros at the end of a number are significant. Zeros at the beginning number don't count as significant. So we say, what's the mass of this item? 0.00072 grams. 0.00072 grams has 5 digits written out, but only 2 of them are significant. Zeros on the left don't count. Zeros that are sandwiched between non-zeros count. So you want to make sure you have this committed to memory. We'll practice this a little bit in the lab this week. And like I said, this can be much easier to handle with scientific notation. Let's say the number 50,000. Let's say we were sure of the first 2 digits of that, the 5 and the first 0, but everything after that was an estimation. So we want to write 50,000 with two significant figures. Well, if I write the decimal point, it's got 5. If I don't write it, it's got 1. So the way to get around that is to write 5.0 times 10 to the 4th. That's 50,000 with 2 significant figures. Now the rounding rule that we've been taught is when we've multiplied or divided two numbers and they have a different number of significant figures, whichever one of them has the least, the one that we call the weakest number, the one that has the least significant figures, will determine how many significant figures the answer has. So we multiply a number that has 4 significant figures by a number that has 2 significant figures. Our answer should only have 2 significant figures. That's all we can be sure of. When we're adding and subtracting, we don't keep track of the significant figures, we keep track of the decimal places. So when we add or subtract two numbers, and we'll practice this in the lab, we will keep the number of decimal places of the weakest number in the calculation. For unit conversions, and this is going to take a lot of practice, we'll do some of this in the lab, we're going to do this all semester long. We know that I am, for example, 5 foot 10 inches tall. That's 70 inches. If we want to know what that is in meters, we're going to multiply that 70 inches by one or more conversion factors. Conversion factors are fractions that are used as multipliers, and the key to a conversion factor is that the numerator is equal to the denominator. For example, there are exactly 2.54 centimeters in an inch. So if my height is 70 inches and we multiply that by 2.54, we'll know exactly how many centimeters tall I am. And then we can multiply by 1 over 100, because there are exactly 100 centimeters in a meter, and we would have my height in meters. And so we'll practice this a little bit in the lecture hall, and then we'll also work out a couple of these in the lab. There are a bunch of problems at the end of chapter 1. These are the ones that I think are most representative of what I'd like us to be able to do from this chapter. And so these are the ones I'd like you to work out. Some of these we will work out together in class, and one or more of these will make up your first graded quiz or assignment that will happen fairly soon. And so check these out, work on them with your friends or with your partners. If you have one that you work out in particular and have trouble getting the answer that matches the back of the book, come to class and ask about that one, and that'll be one of the first ones that I work on the board in class next time.